This is Programming Chapter 2, Part 2. Now, variables are defined with identifiers. And again, the compiler will assign a memory location for that identifier. Then, depending on what you are defining, it's going to use a certain amount of bytes. If the data is the size of the data bus, then we call this a word. So, on a 32-bit CPU, 32 bits is a word. And on a 64-bit CPU, 64 bits is the word. Why do we want variables? Well, computers can really only do one calculation at a time. So if we're doing a calculation that requires several variables, we need to store it somewhere while we're doing other calculations. And the more complex an algorithm, the more variables we'll need to perform an algorithm. An example is if we have this quadratic and we want to do the quadratic formula, well, the user is going to have to input A, B, and C. And we have to store that somewhere. And now we can compute the quadratic formula. Minus B plus or minus the square root of B squared minus 4AC all over 2A. So we're using the stored values to compute the quadratic formula. So your first exercise is to look back at the naming conventions and tell me a little bit about the naming conventions for variables. You don't have to list all of it. Just give me, say, the top 3. Now, functions are also defined using identifiers. And we've already done some in the previous chapter, but the simplest way to view functions is a piece of code that is reusable. So instead of writing several lines of code to find the maximum in one list, and then writing more lines of code to find the maximum number in another list, what you would do is write a function that just finds the maximum number in a list. And we use the list as a parameter to that function. And this is good coding practice because if you do it right, you can just keep using that function without having to get the wrong result. And standard libraries have common functions for us. It's important to understand how to use them and also how to create some of them. So that one's easy to recreate. This one, not so much. And this one, not so much either. But sometimes you're going to be programming and you won't have a library, so you need to be able to create some of these functions on your own. Okay, your next assignment is to tell me what a few of the naming conventions for functions are. Next, printing just strings isn't very useful because it's not making any decisions, it's not making any calculations. So, to make more useful programs, we need to compute or evaluate things. And for mathematical expressions, it follows the rules of BEDMAS. So, 3 plus 4 times 7 minus 12 divided by 2 is actually evaluated as 3 plus brackets, because multiplies come first, minus, and then divides come first as well. So this is 3 plus 27 minus 6, and that's 25. So let's look at exercise 2.0. Actually, this should really say example 2.0, but we'll go ahead and do that. So here we're printing quotes 5 plus 7. We're doing this literally. We don't want to do a calculation. Here we're not using quotes, so it's actually doing a calculation. And here, this is the C way of doing it. This is the C++ way of doing it. And again, here we're printing number, literally. Here we've assigned a variable called number, and we're setting it to 23. And here we don't have quotes around number, so we want to actually print out the value of number. And finally, we have str as a string, a literal string, so it's going to print that out. Here we have a variable called str, and it has a string value that's called, this is a string variable. Here we're printing out str as the variable, not a literal. So let's run this. And we'll compare it to what we have. So we're printing literal 5 plus 7. We're printing the operation 5 plus 7 here, which is 12. And again, 12. Here we're literally printing out number. Here we have the variable number and we're printing it out. That's 23. Here, again, we have a literal string, str. And here we have the variable string and it holds the value. This is a string variable. And that's it for that example. Okay, let's look at the next sample program. This is the program that you'll be modifying for your exercise. Okay, this program sets AA to 78, B to 99, then prints 78 plus 99 is equal to whatever the answer is. We're going to call a function called add, and it will actually add the two numbers and return the value. So let's just run this. And we see that 78 plus 99 is 177. Let's take a look at how this code actually is put together. Okay, so initially, AA and B don't have a particular value set to it. If we step through one line, we see that AA gets set to 78. We step through another line. We see that B gets set to 99. Now, I'm going to set up some watch values. Okay, so this AND sign means the address of AA, and the AND B says the address of B. We can see that it has this memory location, which is a fairly large value. We can also look at this memory location. So we can see that at AA's location, we have 78000. This uses up 4 bytes because it's an int. And these bytes are in little endian format. So it means the lowest byte value gets put first, and the highest byte value gets the last memory location. So this is 78 times 1 plus 0 times 256 plus 0 times 65536 and 0 times 2 to the power of 24. If we scroll up a little bit, we can see the memory location for the variable B. And like I said, the compiler assigns these memory locations for you, so you don't have to worry about where they are. You can just always refer to it as AA and B. Now let's step a little further. Now we're in the add function. We're in the add function because this statement is telling it to go to the add function. Now I'm going to step another one. I'm going to add another watch. So when I say add, it puts AA into this A. It takes this B and puts it into this B. Now remember, B was this location. But if we look at the memory location for this B, it's different. That's because it stores this value into add's own version of B. And add also has its own version of A. So we can see that this is 1AFC98, which is here. And we look at this B value. It's over here, which is different from this location. So there's two B's now. One copy is B is for this add routine. One copy of B is for this main routine. And this is called scope. We'll go into scope a little bit more later. And let's step again, and now we're back to this routine. Every time you call a function and the function's done, it returns back to where it left off. And if we look at the output, actually it won't print the output. And the reason why it doesn't print the output is the text buffer is not flushed. Okay, so that completes that example. You'll need to modify that program to include subtract, multiply, and divide. And this is your sample printout that you should emulate. Okay, again, there aren't too many interesting things that we can do until we learn more ways to control the computer. And this program is called hard-coded values. We set A and B to certain values and we can't actually change it. And to make it more useful, we want to have the user to be able to enter their own values. And when we're asking the user to enter values, we always want to prompt them so that they know what they're entering. And that's especially the case for sentinels. So let's look at sample 2.2. And it does the same thing, except instead of setting A, we're prompting the user to enter the first number, and we're getting it from the console. Again, we prompt the user for the second number, and we get it from the console. So let's just run this. And we can put anything we like, 56, 78. So 56 plus 78 is 134. That looks good. So this, you have to just take my word for it. This is a special function to enter from the keyboard. And this is for C++. You'll have to look at the code for Java and Objective-C in the other videos. So there's nothing you need to modify for this. Just use this and replace the hard-coded values, and you should be able to complete your exercise. Unfortunately, this is still not too useful because it only does it once. What we want to do is to be able to allow the user to do a whole bunch of adds until they're ready to quit the program. And we use a do while and an if statement to check for a sentinel. And again, we're going to explain this later. We just want to be able to create a good program. So just use the sample code as is, and we'll understand it more later. So let's look at that sample program. Okay, let's run it first, and then we'll examine it second. Okay, so we're asking to enter a first number, and Q is the sentinel to quit. So let's just do 56 and 78 again, and we get 134. We can enter another value, 87 and 34. And it continues. And once we press Q, and it should accept lower or uppercase. We shouldn't force the user to use only one. And it's finished. Okay, so let's look at this code. Because we're entering a letter instead of a number, we have to scan this in as a string rather than as a number. And this just checks the first character of the string. So if I run this again, I can actually type quit without it complaining. So all we want to do is check the first character. And if we hit the first character, it breaks and then it exits the program. Otherwise, it just continues as it did before. This function is slightly different because we've already scanned the input into the string. We want to convert this string into an integer. And the important reason for using a string as a sentinel rather than numbers is we don't want to exclude any numbers from the user. So if we use 0 as a sentinel, that means we can't let the user do 0 plus something, or something plus 0, or something times 0. So it's better to use a string sentinel first and then convert it to a number. And your task is to complete this exercise. And that completes part 2 of chapter 2.